La Conferencia Mexicana de Ensayos No Destructivos presenta la conferencia magistral de Steve Strachan.
So, my name is Steve Strachan. I work for Edify Technologies. Edify Technologies is a manufacturer of a lot of different types of NDT equipment, ultrasonics, eddy current, MFL, a lot of the main NDT methods that are used today. A number of the products are over in the display room. But what we're going to talk about today is what many of you may not know Edify for the other side of the business, which is more monitoring instead of inspection. And in today's world, inspection and monitoring get used interchangeably, and they're really two very, very, very different things. So what I'm going to talk about today in my presentation is how folks are using inspection to drive monitoring in everyday industrial and geotechnical applications. I'm a pictures are worth 1,000 words person, so there's lots of pictures. So the world's getting old, right? So the bridges have been around for 30, 40, 50 years. Pipelines, refineries, petrochemical plants, they're all very, very old. And we need to spend more and more time doing inspection to keep them online so that trains can keep flying, can keep going over the tracks, so airplanes can stay in the air. And inspection just isn't quite enough because it's a snapshot in time, and as these assets get older, we have to do more and more inspection, which is more costly, takes more time, more safety risks. And so the industry's starting to pivot to say, how can we do less inspection or use inspection to tell us where we need to monitor? And by monitoring, I mean doing it without having to send people into the field to take these readings. So I'm going to give some examples about how monitoring technology is being used in railroads or refineries or pipelines or on bridges, and you can get a feel for what is taking place using, in a lot of cases, wireless technology, battery technology, things like that, to push the envelope of technology. As I mentioned, Edify is a manufacturer of a lot of different NDT methods. Obviously, the UT and eddy current. They do a lot of work in nuclear steam generators, robotics, automated vision systems, and also remote monitoring. So remote monitoring is what we're going to focus on today, and we'll give you some examples about the technology and how it's used in practice. So as I mentioned before, inspection is a very, very different thing than monitoring. As you can see from the different folks in the pictures over here, hanging from ropes with thickness gauges, or hanging from ropes on a bridge, or taking manual UT readings on a really warm summer day, or climbing inside of different tanks and vessels, or being put in precarious positions, in the middle of winter. This is all inspection. And as the world gets older, we're having to do more inspection, which is more costly, which is forcing folks to think about how to do more real-time monitoring in lieu of inspection or in conjunction with inspection. So before, what we had was inspection. Perfect. So instead of sending people into the field to take inspections, we can now put sensors. So here you can see some examples of, this is a wireless ultrasonic sensor. So where before you would send a person into the field to take an ultrasonic reading with a thickness gauge and a transducer, in this case, there was an inspection that was performed, and the inspector identified this area. Why does it do that? maybe I'll stop using the laser. They found this area of the pipe that had the most severe thinning and wall loss. So instead of sending someone into the field every day or every week or every month to go take a manual thickness reading to try to understand how fast it was corroding, the refinery elected to put the sensor, actually it was the inspection, the technician who said, you don't need to send me out here every day to go take these readings. Why don't we put a sensor here and it'll wake up every day, multiple times a day, and take a thickness reading, and you can plot thickness over time and understand how fast the asset is corroding. So that's just one example of sensor technology. You can see here over on bridges, sensors are put there to look at fatigue or motion. On railroad tracks, you can see on all the different struts, they're putting sensors to monitor if different train loads and different speeds will affect the rail tracks from cracking or from movements, right? So instead of sending people into the field, a lot of industries are starting to elect to use technology to do these same things. And I'll talk a little bit about each one if my remote will work. Not so fast. One more. There we go. So we'll talk a little bit about some examples of infrastructure monitoring, bridges, dams, tunnels, some earthworks examples. So this would be situations where there's an earthquake or there's a slope movement or an avalanche, things like that, and they want to be monitoring for, earth issues. Transportation, so railroads, pipelines, and just everyday paved roads, looking to inspect and monitor. And then finally, refineries, chemical plants, and power plants. So, geotechnical monitoring. So this is not NDT, so we're going to take a step away from NDT for a minute, give you guys a breather. So we've probably heard a lot about NDT today, so we can go home and tell our families we learned about something else other than NDT. So this is an example of different types of sensors that are placed perhaps on the side of a hill, so it's monitoring for if a rock would fall or if there would be an avalanche. What happens is each one of these sensors is on a pole, and if something hits that pole, it'll wake up and it'll start listening and looking for rock fall or different types of things moving towards the rail, because obviously we don't want to have a train come through with a boulder sitting on the railroad tracks, or else that's going to be a problem, right? So instead of having to send people out to go drive the railroad to make sure that there's no issues on the rail, they have sensors there that wake up whenever there's an issue and say, hey, let's take a look. And then what happens is they have these hubs that if any of these sensors wake up, this hub will take a picture of the area underneath the sensors and send a picture back to the railroad that says, hey, there's a boulder in the middle of your railroad, don't send a train. Right? Am I making sense? See? Kinda. Steve, you're crazy? Okay? I've had it before, believe me. And then some other examples. Putting sensors on tunnels. So a lot of the tunnels that are out there are very, very old, and they need to monitor to make sure they're not moving or they're starting to breathe as they get older, especially as they're doing construction on a lot of these tunnels. What they'll do is they'll put sensors in and around the tunnels to make sure that they're not moving one way or the other if they're digging ditches or if they're doing anything around the tunnel to make sure they're not moving. So a lot of these sensors are waking up to detect movement of any kind. So the tagline is, if it moves, we'll see it, right? So that's an example of geospatial monitoring. There we go. So this is a video, so it's a pretty long build up to the exciting part, so I'll just keep talking while the video goes. But so watch as this, what happens is every one of these sensors is starting to communicate. So they'll wake up like once a day or so, and they'll say, hey, nothing's happening, they'll go back to sleep. if something happens and one of them gets bumped, it'll alert all the other sensors and say, hey, I just got bumped, everybody be on the lookout. And so they'll all start flashing and they'll wake up more and more. And this picture over here is actually coming from this station. And when there's an issue, the picture will show up and they'll send this to the railroad and they'll say, hey, we have a problem, right? Make sense? Easy, right? I was like, Steve, this isn't rocket science, I know. Don't worry, I have another video for you too. If you love that, you're gonna love the next one. Go to the next slide, please. And so just so you can tell that I'm not making this up and just showing you fun videos, this is actually real life. People are actually doing this. So you can see the sensors mounted on stakes, right? This thing's got a mind of its own. Over here on stakes, you see these sensors. And so they wake up and let the railway know that it's safe to send trains. Next slide. Bridge monitoring. So similar story, right? Bridges aren't getting any younger. We want to make sure that when people drive over bridges that they safely get to the other side. A lot of these sensors are looking for sways or movements or corrosion in some cases. Edify doesn't do it, but there's acoustic monitoring that's available where it's listening. So there's a lot of different technologies that are being deployed, on a lot of different infrastructure to be able to monitor it without having to send people. Next slide. Same story, you saw some of the pictures of these sensors that I had on the other picture. So they're putting them on like every 10 feet. And what's happening is these sensors are they're actually tilt sensors. So anytime that they move this way, they wake up and they alert and they measure and tell you how much they moved down to 1 millimeter accuracy. No, sorry, 0.001 millimeters of accuracy. It's crazy. Like if the train goes by and it's got a heavy load on it, it'll wake up, it'll notice the rumbling from it. And then they'll tie that off compared to when the sensor woke up. So they're very, very, very sensitive. And then there's a sensor that you can put a laser, and the laser will measure the distance to the track. And if the track moves at all, the laser will measure any movement in the track, because if the track's moving, we don't want to probably send the train because it could potentially crash. So not only is it measuring tilt, but it's also measuring distance, which is really kind of cool. Next slide. There's other technologies. So folks that know me know I'm a history nerd at heart. I love studying like civilizations of the past. In Brazil right now, they're using LiDAR on helicopters to map out the Amazon rainforest to look under the canopies of trees for previous civilizations. That same technology is being used on railroads. And you figure you put a LiDAR scanner on either a car or on a truck, and they drive hundreds of miles and scan every inch of the railroad track, looking for cracks, sediment buildup, whatever you're looking for. And we're talking hundreds of thousands of gigabytes of data that the railroad's getting from doing inspection of these tracks. And so what they're now doing is feeding defect size, different types of simulations and different types of issues to all of this data, so that as they run over the track, the AI will flag when there's a problem so that they can send a maintenance team out to fix it before there is an actual issue. Pretty cool, right? So here's some examples of what that data kind of looks like. Next slide, please. As promised, here's your other video of just how this happens in real world. So you can see this is actually a truck. This is one of those LiDAR cameras that I was telling you, right? And so they're collecting a ton of data as they drive down the tracks, and they're mapping it all out. And when they see a crack, or if they see a broken tie, or if they see sediment buildup or anything that they think could be a problem, they're flagging it so that they can proactively fix a problem before it becomes a problem, right? So there's some extra sediment buildup on the side of a tire. If that goes too long, it could derail or could push the track back, derail the train. So it's measuring how much sediment, what the space is between the rails, and they're doing it, and a lot of times real time as they're driving over the tracks for, you know, tens to hundreds of miles. So again, pretty cool stuff. I'm a nerd. I thought it was neat. But look up that LiDAR in the Amazon rainforest stuff. It's so cool. They're learning so much about like different civilizations that they never knew were there in the Amazon rainforest. And they've been at it for like 3 years, and they've done like 1% of the Amazon rainforest. It's crazy. Next slide. And my last segment is on energy infrastructure. So this is probably, you know, again, more near and dear to our NDT hearts, with power generation, nuclear power plants, refineries, petrochemical plants, and even wind turbines. So we'll talk a little bit about how the technology is being deployed across those spaces. Next slide, please. So this is an example in a refinery, petrochemical plant. So here in Mexico, Pemex has, I think it's 7 refineries across the country that are responsible for the majority of the oil refining that goes on in the country. And these folks have spaghetti bowls of pipes and tanks and vessels that are constantly being inspected for corrosion or erosion. And so what's happening in refineries is, whether it's a robotic inspection or whether it's a personal inspection, they're going and finding locations that are critical areas, elbows of pipes or on tanks and vessels, and they're coming back and putting a sensor so that they can map thickness over time. And I'll show you what that looks like in a second. But on the right side, you have a sphere, you know, or a large diameter asset that's held on with a couple of magnets. And the other sensor is like a 20-inch pipe that you have a wireless UT sensor on top. They're battery powered, they're fully wireless. The one on the left can live up to 950 degrees F. Can you guys hear me? Yeah. Sorry. Is that better? Sorry. I just get so excited. The sensor on the left will live up to 950 degrees F, 500 C continuously. So very, very hot process piping, which is a lot of times what you have in refineries. And then the other one is held on with magnets for lower temperature, larger diameter assets. Next slide, please. And so this is where the rubber meets the road, is the data. So thickness is on the y-axis and time is on the x-axis. And so what you see is over the course of a year, this is a trend line of daily thickness readings, right? So that sensor is waking up and taking a reading at the same place over and over and over every day for a year. And it's plotting what's happening over time. So you can see these boxes are different corrosion rates over the course of a year. So in a lot of cases, corrosion is a non-linear event, especially in refineries, depending on what crude slate they're running, what temperature, what pressure, what chemical inhibitor they're running. It could be at what pH level it is. There's a myriad of different inputs on how these refineries operate, and every one of them could be a different corrosion rate. So for example, this box here for my friends on the left side, on the right side, if we run like this for a full year, we're gonna have a very significantly different corrosion rate, and the pipe might only last 3 to 5 years. If we operate like we do on the down here in the corner, the pipe could last for 25 years, right? So corrosion rate here in the middle, malo. Corrosion rate here on the right, bien. So it's these refineries are learning more and more every day about how best to run and operate their plants so that they don't have leaks and spills and downtime without having to send people into the refinery to do inspection. Make sense? All right. Next slide, please. Similar story. The only difference here is on the other y-axis is temperature. So these sensors will take a skin temperature as well as a thickness reading. So you can start to correlate temperature versus corrosion rate. So over here, when the temperature was high, the corrosion rate was high. When the temperature was low, there was literally no corrosion. So the refinery was trying to tweak what is the optimal way to run my refinery based on the temperature, and so you can see it tweaking. So that's all just coming from the sensor. Crude slates, pressures, temperatures, other kinds of inhibitor dosing are all other inputs that get stacked on top of this data to help give the refineries or chemical plants the best idea how to run their assets. Next slide, please. I mean, I can try, but we don't want that to happen. So this is on a pipeline. So this just so happens to be an above ground pipeline. Many pipelines, as we know, are below ground. Typically, pipelines are inspected using an ultrasonic pig. Right? It's a big apparatus that gets put in the pipe and sent, many kilometers or miles to do a full inspection of that pipeline. And then they dig up different areas of the pipeline to do manual inspection, compare the pig results to the manual inspection results, and then make a decision of, do I need to replace my pipe? How long will it last? Do I need to increase my inspection interval? Well, what's happening now is it's not cheap to dig up a pipe in the middle of nowhere. It usually costs, $25,000 to $100,000 to maybe even more just to dig a hole to send people into a ditch to do an inspection. And then when they're done, they would just cover the hole back up. Well, so what's happening now is these pipeline owners are leaving sensors behind with a cable to the grade. And once a month or once a quarter, they can send a person out to just go collect in and get data without having to dig up that pipe anymore. If we have other systems that you can put a transmitter hub above ground and it can be wireless. But if you're going to spend all of that money and all that time to dig a hole, why not leave something behind so you can monitor it? And that's what's happening here in the midstream pipeline area. Okay, next slide. This is a fun one. So wind turbines, right? All those windmills you see in places like West Texas and all over Europe. The blades are the ones that are moving, good. The ones that are not moving, bad. So there's a lot of focus on making sure that that propeller keeps turning, right? So what we do is we put sensors. So this is the gearbox on the left side, right? And this is like a crankshaft. So these can be like 6 feet, 8 feet long, about like that, right? And so what we do is we put transducers permanently on the back part of the shaft, kind of like pepperonis on a pizza, right? And they will shoot ultrasound from the gearbox all the way to where the blade is. And if they get a response echo, good, no problem, right? So this would be a good example of a good crankshaft. And then here you have an example of oh, wait a minute, we have a back wall echo in a place that we didn't have before compared to one that's a lot longer, which means we might be seeing a crack coming through the gear shaft or the crankshaft. And then the last one is a picture of, so when they see this, they know that in this situation, they better get out there and go fix it because they don't want this to happen, right? Because if that happens, the turbine stops spinning, right? So that's monitoring crankshafts. Next slide. And they also monitor the blade. So you can just see a portion of this blade. You've seen these blades on the back of big rigs and trucks. They're the length of this room, big composite blades. So every one of those blades has a ton of bolts that are connecting it to the crankshaft. They're actually putting sensors, each one of these is a sensor, that's looking at the area where the bolt ties into the crankshaft to make sure there's no cracking between the bolt and the composite fixture. So as it's turning, they've identified areas of failure where it typically starts to delaminate, and so they're putting ultrasonic sensors there and monitoring as it goes around. Cool, right? Does that make sense? Yeah? I think I have one more slide for you, maybe. Next slide. Oh, this is a cool one. This is my last one, I promise, and then I'll get off the stage. Nuclear power plants, right? So nuclear has become a really, really big thing in the last couple of years because of the power demand from AI, LLMs, all the quantum computing that you hear and read in the newspaper with Elon Musk and the Amazon people, and everybody's doing a lot of chat GPT, right? So the nuclear power plants are being told you can't go down, we need all the power we can possibly get. And so the good news is the power plants, the nuclear power plants are finally making money again, so that's good, right? The bad news is their shutdowns, they used to have two, right? One in the spring, one in the fall. They started condensing them down to just one really big outage a year, and so they've got to get a lot done because they can't afford to shut the plant down. They have in every nuclear power plant what's called ESW lines, emergency sour water lines. So they're basically, if there's a meltdown in the reactor, they open these lines and they flood it with water to cool the reactor. Every one of, and it's rare that they test these ESW lines, these emergency water lines. And so what happens is over time, air bubbles will accumulate at the top part of these pipes. And if they turn them on and these air bubbles race to the pumps and the compressors, they'll cavitate or dry them out or make the pumps stop working. It'll seize them, in which case water can't get to the reactor to cool it down. So for the last 15 years, there's every BWR and PWR in the world has between 100 and maybe 250 locations, which is mandated by the local government to go be inspected manually to make sure that the pipes are full of water and there are no bubbles, right? So today, and this has to happen every quarter in most cases, so 4 times a year at 200 locations at every plant in the world, right? And all it is a person's got to dress out. A lot of times it's in radiation dose environment places where you don't want to send people. A lot of times they have to dress out and carry ladders down 3 feet of stairs to get into the reactor core to go just take in an examination where they're taking a flaw detector and a transducer, and just going presence of void or not, right? And so it takes a lot of time and energy. So they said, why don't we use a sensor that we can just put on the top of the pipe, and it tells us we either have a back wall, which means pipe's full of water, or we don't have a back wall because the air pocket is keeping the ultrasound from going to the other side of the pipe and back. So now, really in the last 2 years, what was a very manual process for every single nuclear power plant in the world is now an automated system that we're moving towards an automated system where they don't have to send people into bad dose heavy in places, and everybody has plenty of work to do, so we can find places to have people do other work. So this is my favorite one, and this has really just come about in the last 1 to 2 years. I was just at a nuclear power plant last week in Pennsylvania, And the entire executive team was just saying, how quickly can we do this? It just makes too much sense. So, cool stories. I think that's it. I promise, I hope. Maybe. Oh, here's just some pictures. Yeah, so this is just a picture of some of those sensors. So you can see, this is a gentleman who runs the Wolf Creek Nuclear Power Plant in Missouri. This is one of our engineers who might look familiar to some of you in the room. But what this is like a 14-inch pipe that we filled with water, and then we put a sensor on the one side, and it's shooting from one side of the pipe to the other, right? And so if you put your hand in it, it simulates a gas void or a void, and you don't get an echo. So those are the sensors, right? And they're just doing some testing. So this is, like I said, this is brand new in the last year or two. And I think that's it. That's it. Yeah, thank you guys for your time.